Hi everyone, we have built a soccer data analyst agent that lets you ask anything about the Club World Cup from top scorers to match stats and helps you get instant answers. For example, let's ask who are the top 5 goal scorers in the Club World Cup. You will see the agent's full reasoning. It interrupts the question, rewrites it into a structured query and calls the right tool within the MCP server and returns the response. And the best part here is this is all running locally on my machine. We started by loading a Club World Cup data from CSV files into local SQLite database that's served via the FastAPI backend. On top of that, we built an MCP server with custom tools that can read from and write to the database. And everything is running locally here. But here's a big question. How can cloud-based agents or applications can securely call my local MCP server or model without even uploading anything to the cloud? That's where local runners comes in. Think of local runners like ngrok, but for AI workloads. They let you expose local models or MCP servers to the cloud via a public endpoint, so agents can call them as if they are fully deployed. You can test, debug, and validate everything right on your own hardware. In this demo, the database and MCP server are entirely local, but fully accessible. We will walk through how local runners makes this possible in this demo. Now let's jump into the code. First, let's take a look at the FastAPI server. It exposes the local SQLite database of Club World Cup data, including clubs, players, and matches, all loaded from CSV files. You can see we have 3 different CSV files: matches.csv, players.csv, and clubs.csv. So we start by setting up the database URL and initializing the SQLite engine. Then we define the Python classes using SQL model, which represent our database tables like club, player, and match. Next, we use the async context manager to create tables and load CSV data if the database is empty. Finally, we define the endpoints to read and write club, player, and match data. This FastAPI server becomes the core backend that the MCP tools will interact with. Now, let's take a look at the MCP server. You can see the folder SQL MCP Server. This is the project structure that you need to follow if you want to create a custom MCP server using Clarifai. The subdirectory 1, and within that we have the model.py file. This is where we specify the MCP server logic. We initialize the FastMCP server that connects to our local FastAPI backend. This is the FastAPI base URL we will get once we run the FastAPI server. And we then define the tools like get club info, get all clubs, get match info that internally call the FastAPI endpoint using this make API call. So these tools handle querying clubs, players, and matches using the filters like name, year, or stats. And at the end, we expose the server via the myModel class, which Clarifai uses to run this MCP server. And also we have the config.ml file, which contains the metadata and configuration settings, such as compute requirements needed to run the model, and also the requirements.txt, which lists the Python dependencies required to run this MCP server. Before we run this MCP server using local runners, let's take a look at the front-end logic as well, the Streamlit file. You can see here we are using Crew AI as an agent framework, and here we are defining the Clarifai MCP server URL. So this is the endpoint you get after running the local runner, which exposes you a SQL backend MCP server as a toolset. And when a user submits a question, we kick off the agent orchestration. In a separate thread, the agent connects to the MCP server, selects the right tool, and builds the structured response based on the data. You can see the complete logic here. We have defined the agent, task, and then running the agent. And finally, here's the Streamlit UI that handles the full chat experience, showing the agent's thought, real-time output, and the final answer. And also, if you just notice, we are using the GPT-4o model from the Clarifai community, which brings the reasoning to the agent's response. So that's the complete Streamlit app and the agent orchestration. Now let's walk through the full local development flow on how you can run this FastAPI server, the MCP server using local runners, and then the Streamlit app. I have opened 4 different tabs in my terminal. First, let's get the FastAPI server running. So this is the command to run the FastAPI server. Ubiquon FastAPI, this is the file name, and I'm just running the command. And our FastAPI server is up and running, and this is the URL that we could use to interact with it. Now next, let's launch the MCP server using the local runners. I'm going to use the command Clarifai model local dev, which is gonna soon change to Clarifai model local runner. But yeah, let's run this command. Once you run the command, local runners wrap your MCP server code and expose it through a callable public endpoint, allowing agents or APIs to securely interact with your tools and logic even when everything is running locally. If you're running this for the first time, you will be prompted to set up a context, which includes details like your user ID, personal access token, and other environment variables. Since I've already configured the context for my local runner, it will just use that to start the server. So you can see the full model URL here. This is your MCP endpoint that the agents or APIs can call to access the tools you have defined in your local server. And also you can even use this code snippet to test this endpoint. To confirm everything is working, let's run the client.py script. So we have a client.py that we have defined in our code as well that demonstrates the MCP server's ability to communicate with the FastAPI server and retrieve data. So I'm gonna run Python client.py. You can see it's just calling the MCP server and printing the tools which is available, which we could access. You can see these are all the tools. And yeah, our MCP server is up and running using local runners. And finally, the Streamlit app. You can see the app is already up and running. The biggest advantage of local runners is rapid prototyping. You can make quick changes and you can test it out without even deploying to the cloud. So you can see for this query, the agent is calling the get top scorer underscore CWC tool within the MCP server. Let's quickly go to that and modify it and test it out. For example, let's modify this get top scorers underscore CWC. This is the tool that the agent calls. Instead of returning all the, like you can see, just returning all the player info, goal scored, and all the details. So instead of that, I'll just change it to just to get the player name. If someone asks for the top 5 goal scorers, it just gives a player name. Now I'm gonna save this. I'm gonna go back to my terminal. I'm gonna go to the local runners and I'm gonna run this again. Now let's go back to the Streamlit app and let's rerun this. And let's ask the same question. Who are the top 5 goal scorers in the Club World Cup? You can see we just got the player name. You can see the changes reflected by simply restarting the local runner, all without needing to deploy anything to the cloud. That's how local runners helps you do rapid prototyping in all your applications, models, or MCP servers. Also, local runners offer several key benefits. First, they provide flexibility. You can run models anywhere Python is supported and there's an internet connection, whether it's your own machine or an on-premise server. Second, they let you leverage your own local compute, which is especially useful if you have a powerful hardware, reducing reliance on a cloud infrastructure for development. Third, they help you connect your locally running models to Clarifai's compute plane, enabling secure interactions with the cloud-based agents and workflows. And finally, they are ideal for rapid prototyping, as we have seen in this example, allowing quick iterations, real-time debugging, and fast validation of outputs without deploying to the cloud. So that's all for this demo. Thanks for watching.